method. Ok, so un de 200 plus étudiants se plaint de mon accent en français. Donc, je vais, et elle demande que je parle anglais et elle m'assure que tout le monde comprend anglais. Ok, on va voir. Mais en tout cas, j'ai le texte en français. Donc, ce que je vais faire, c'est je vais parler en anglais, mais en suivant le texte en français. Si je fais un commentaire supplémentaire en anglais, je vais aussi le dire en français. Parce que sinon, il y a plus en anglais que en français. Okay. So here we go in English. Or laissez-moi juste dire, si vous ne comprenez pas mon anglais, c'est pas du tout grave, juste m'ignorer et ignorer ma voix et écouter, lire le texte. Sauf quand je commençais de parler français. Peut-être je vais lever la main quand je parle français. Okay, so we were talking about the Big Bang and in particular, the expansion of the universe. So if all the galaxies are flying away from us and with respect to each other, that implies that in the past, they were all closer together, just rewind the clock. And so the density of matter and energy in the universe was higher, right? So cosmologists think, in fact, 13.7 billion years ago, that's 13 decimal with 7 and then 8 zeros after, the density approached infinity. So we say that the universe approached a singularity in density. In fact, it was a singularity in density and many other factors, the temperature, the pressure, the energy levels, and curvature, maybe most importantly, the curvature of space-time. So je dois le dire en français parce que il y a aussi les autres choses qui s'approchent à l'infini, or l'infini, c'est par exemple la température, la courbure de l'espace-temps, la énergie, la densité d'énergie, tout ça s'approche à l'infini. Et donc, c'est ça qu'on appelle dit la singularité, c'est ça. C'est ce moment où les choses s'approchent à l'infini. Plusieurs facteurs s'approchent à l'infini. Okay, so to make this extrapolation in a quantitative, precise manner, you have to take into account how the expansion rate changed with time. And this is governed by the Einstein's equation. And the general theory is called the general theory of relativity, or Einstein's theory of relativity. The problem is we don't know how to deal with an infinite density or an infinite curvature either. And we don't know how to deal with any infinity in our theory. Nous ne savons pas comment traiter les infinis dans notre théorie, la densité, la température, la courbure de l'espace-temps. So this singularity poses a sort of limit to our understanding. I've said this is the Big Bang for philosophers. I just want to make a philosophical point that how do we understand this sort of limit to our understanding? Well, you could say that the theory of general relativity is only valid after a certain time period, some time period after this singularity. So we just by convention, we say that time starts at this singularity. We say that's time t equals 0. And but our laws only apply at a time scale of the order of the Planck time, TP, which is about 5 times 10 to the minus 44 seconds. So the tiniest fraction of a second is the Planck time, and we say our laws only apply after this Planck time, after the singularity. And so we can, in principle, only explain the universe after TP or a Planck time after the Big Bang singularity. We don't have the tools to deal with earlier times. So je pense que la seule chose que je n'ai pas dit écrit dans les diaporames, c'est que par convention, on dit que l'instant de singularité, c'est t égale à 0, juste pour avoir un début net t égale à 0. Mais il faut admettre que nos outils mathématiques, ils n'appliquent que TP, un temps de Planck après cette singularité. Another point is you can ask what happened before t equals 0, what happened before this singularity, and the answer is we just don't know if time even existed before the Big Bang. Okay, the standard cosmological model starts with this Big Bang, this t equals 0, which with respect to now is about 13.7 billion years ago. It's a quantitative model after a Planck time, after this singularity, and it's described by the fundamental laws of physics, admitting that as we approach the singularity, the laws become more speculative. We don't have the possibility of making laboratory experiments to verify the properties of matter at such high densities. So what does that mean for our knowledge then? Well, it means that we're doing a sort of quantitative extrapolation based on laws that are verified in the laboratories at much lower energy levels. Which energy levels? Well, the energy levels of the particle accelerators in the largest particle accelerators in the world, like you'll find at the CERN lab in at the border of France and Switzerland, or at the Fermi lab in near Chicago in the United States. So je dois le dire en français, les plus hautes énergies que nous pouvons créer ici sur Terre, c'est dans les accélérateurs de particules comme se trouve à le laboratoire au laboratoire de CERN, à la frontière de la France et Suisse, ou autrement, il y a plusieurs partout dans le monde, mais les plus connus sont CERN et Fermilab aux États-Unis. The model standard standard cosmological model explains many observations. The three principal ones are the expansion of the universe, the cosmic microwave background, and the proportion of the light elements, above all hydrogen and helium, and their various isotopes, their various stable isotopes. Je vais ajouter que il y a des autres observations aussi expliquées par le modèle standard cosmologique, mais ici sont les trois principaux observations, principales observations. Et j'ai ajouté aussi que les isotopes ici doivent être stables, évidemment. Mais il y a plusieurs isotopes stables, par exemple deutérium. For example, deuterium for hydrogen. Okay, one nice question I think every student or even many children ask themselves is the universe infinite or not? And the answer is we don't know, and here's why. La réponse est qu'on ne sait pas, et je vais vous expliquer pourquoi. But, so I talked about the number of visible galaxies, right? That qualifier visible is important. Why? Well, I'm going to explain. There's a sort of distance beyond which we cannot see, something called the cosmic horizon. So the universe has an age, as we've just said. We think it's 13.7 billion years old. And during that time, light traveling at a finite speed can only travel a finite distance. So that implies we can only see a certain finite distance away, no matter where we look in the universe. And so we call that the horizon, the cosmic horizon. It's analogous, if you like, to the horizon you see when you look out to the ocean. You can't see beyond a certain point because the Earth, in that case, it's because the Earth is curved. Here, it's the cosmic horizon is for a totally different reason, but it's a limit nonetheless to how far you can see. And that distance is approximately 13.7 billion light years. It's not exactly that because, well, for reasons that are not too important for us, but it's because during that time the universe has been expanding, so the calculation is a little bit complicated. But it's approximately that time period times the velocity of light, which gives you simply 13.7 billion light years. So j'explique en quelques détails qui ne sont pas vraiment importants, mais juste pourquoi j'ai dit environ 13,7 milliards d'années-lumière, c'est parce que pendant cette période de temps, l'univers était en expansion et donc le calcul de distance qu'on peut voir dans cette période de temps, ça devient un peu compliqué. Mais c'est vraiment les détails. L'idée essentielle, c'est qu'il y a une limite de distance maximale qu'on peut voir avec la lumière dans un univers avec un âge fini. But I'm actually speaking in English now, but our standard cosmological model, or the standard cosmological model, makes a hypothesis that the universe is homogeneous, meaning it has these properties that are the same everywhere in space. For example, the number density of galaxies per unit volume. But that doesn't mean that there's necessarily an infinite number of galaxies, right? Because space itself does not necessarily have to be infinite. In fact, space can be finite, homogeneous, and isotropic, so independent of direction, without a border, without an edge to the universe, if you like. I understand that this is counter your intuition that you've built up with experience of a sort of Euclidean world, a Euclidean geometry, if you like. But there are more types of geometry than Euclidean geometry. There are geometries that allow this possibility of a finite, homogeneous, three-dimensional volume. And so that's what I'm going to explain now. So je l'explique en français. En fait, c'est contre l'intuition qu'on peut avoir un espace de volume fini, mais sans bord, qui est homogène en fait, isotrope même. Mais c'est contre l'intuition parce que nos intuitions viennent de l'expérience avec la géométrie euclidienne. Mais ici, cette géométrie n'est pas du tout euclidienne. C'est ça le problème intellectuel. Je ne veux pas rentrer dans tous les détails de la géométrie courbe de la relativité générale, mais je veux vous donner une petite idée de la géométrie qui permet un univers avec volume fini, mais quand même homogène sans bord. Okay, so there are 3 types of universes, in fact. The first one is what we call a closed universe. It has a finite size and a positive curvature. The second type of universe has a flat geometry, but it has an infinite size. And finally, there's a third universe, which we call the hyperbolic universe. And it again has an infinite size, like the second one, in contrast to the first one, but its curvature is negative. Unfortunately, we don't know which type of universe we inhabit. It depends on the density of all the forms of matter and energy that are in the universe. So I'll speak of the different types of matter and energy in the universe. In fact, there are 3 types of matter and energy. En fait, je viens de remarquer, je parle de la matière et énergie. C'est comme en anglais, je fais la conjonction de les deux, matter and energy. So matière et énergie. Avec la théorie de relativité, comme vous le savez, il y a l'équation renommée d'Einstein, E égale mc au carré. Ça dit en fait que l'énergie, c'est une sorte de forme de masse. Et en fait, l'énergie peut avoir la masse, les propriétés de la masse. En fait, même la chose importante ici pour la cosmologie, c'est le fait que même la lumière qui gêne mes yeux maintenant, c'est la lumière... ça fond de gravitation aussi. Et les autres formes d'énergie aussi, la pression, la température, tout ça, ils sont les formes d'énergie et ils sont subis et ils créent la gravitation. So in fact, I said much more in French there, so I'll say it in English too. The matter and energy both are subjected to gravitation and they create gravitation. So in Einstein's theory of gravity, we have to include both energy and matter in the discussion of gravitation, and that's really what's important here for deciding what type of universe we have. Okay, so there are three types of matter and energy. We'll start with the simplest one, the standard model of particles describes the familiar matter that's composed of the elements that you find in the periodic table. So composed mostly of, or almost entirely of neutrons, protons, and electrons. And in fact, in equal or almost equal proportion. But this, what we want to call ordinary matter, only comprises about 5% of the total matter and energy in the universe. There's another, so what's all the rest? Well, there's another 25% of the matter and energy in the universe is what we call dark matter. And it's a mysterious type of matter that is, all we know about it is that it's different than this ordinary matter. And but it's necessary to explain the dynamics of galaxies. And I wrote here in French the internal dynamics of galaxies, by which I mean the movement of the stars within the galaxy. But I should add, I think I haven't added it in here, so I'll just say it in words. It's also the dynamics of the galaxies themselves within a cluster of galaxies. So je l'explique en français. J'ai dit les dynamiques internes, ça veut dire des galaxies, ça veut dire le mouvement des étoiles dans la galaxie. Mais je dois ajouter aussi la dynamique des galaxies eux-mêmes dans les amas de galaxies, les groupes de galaxies. On a besoin de la matière noire pour expliquer les dynamiques comme ça. Okay. The third type of matter and energy is what we call dark energy in English, and it's a form of energy that's very strange, perhaps even stranger than our dark matter. It's very distinct from the dark matter, and it's necessary to explain the acceleration of the expansion of the universe, which was discovered in 1998, or the result was published in 1998. Je vais juste ajouter en français que peut-être cette énergie sombre, c'est bien plus mystérieuse que la matière noire. C'est bien différent. Notez bien que c'est nécessaire pour expliquer l'accélération de l'expansion de l'univers. Yeah, c'est autre chose. Okay, so it's this dark energy is different than the dark matter. You could say that it's one of the great open problems of fundamental physics to understand the nature and origin of both dark matter and dark energy. So I guess those are two problems. You could say these are two open problems: to explain dark energy and to explain dark matter. So c'est deux problèmes bien distincts, bien différents. Bien différent, le problème d'expliquer la matière noire et l'énergie sombre. Ce sont toujours les problèmes ouverts. En fait, je propose les projets de L3 physique. Ce n'est pas pour vous si vous n'êtes pas dans la physique, mais c'est pour les étudiants de la L3 physique. Je propose les projets pour étudier la matière noire. So I just said that if you happen to be in physics in third year, then you have the option to follow a reading project where we study dark matter. Okay, the formation of galaxies. The universe is supposed to be homogeneous at times near the Planck time, and during the Big Bang and afterwards, or shortly thereafter. But we need fluctuations in the density, right, in order to be able to generate finally or eventually the galaxies that we have observed. We do expect fluctuations in the density due to quantum mechanics, but those are just quantum mechanics on its own is insufficient, to explain the density fluctuations that are necessary to create galaxies. They're just insufficient. They disappear too rapidly. So physicists have been thinking about this a long time, and they've come up with a proposed solution. It's perhaps just a hypothesis, but it's become a standard part of the model. It's called inflation, and it's what it means is a period during this very early in the universe during which the expansion was very rapid. It was proposed in the early 1980s by a then young physicist called Alan Guth. And this hypothesis, actually, this inflation hypothesis, resolved actually several problems in cosmology. One of these problems was this problem that we're currently talking about. How do you get density fluctuations large enough that they can form the seeds from which galaxies eventually grow? And this inflation helped in that you could imagine that the quantum mechanical fluctuations were then frozen and greatly expanded in size during the inflation period. And then this would make them sufficient to generate galaxies. So however these fluctuations were created, whether it's by inflation or in another process, in any case, we can observe these variations in density, and they actually I'm going to update this. It should be 300. Well, there's it's between 370 and 380,000 years after this t equals 0 time of the singularity of the Big Bang. And how can you observe these variations in density? Well, you look at something called the CMB, which I explained earlier is the cosmic microwave background. And these variations in density lead to the, via gravitational attraction, finally produce galaxies. So j'ai précisé que c'était environ entre 370 000, 100 000 et 380 000 années après le t égale 0 aux singularités de du Big Bang. Okay, now I'll talk about the formation of the elements. So before about 1 second after the Big Bang, the universe was a sea of elementary particles: protons, neutrons, electrons, photons, the particles of light, and something called neutrinos. They're another elementary particle. But before about 1 second after the Big Bang, the temperature was just too hot to form the nuclei of atoms. The kinetic energy of these elementary particles was so large that it was, in other words, the temperature was so hot that they would hit any nuclei that were in the process of trying to form, and they'd break them apart. So the nuclei could not form in this hot environment. But then after about 1 or 2 seconds after the Big Bang, you have to bear in mind that the temperature is dropping as the universe is expanding. And so the temperature had dropped enough that the energy of those particles was small enough that you could form the nuclei of atoms. And so the form they did, the neutrons and protons joined together and produced the nuclei of elements, mostly up to as complicated as helium-4, the principal isotope of helium, which contains 2 protons and 2 neutrons. And peut-être je vais juste signaler en français que j'espère que c'est clair que lors de cette expansion de l'univers, la température baisse, n'est-ce pas? Parce que l'expansion de l'univers va baisser la température de l'univers. Et de plus basse température, ça implique l'énergie des particules devient plus basse, et il y a 1-2 secondes après le Big Bang, l'environnement était assez froid. C'était toujours quelques millions de degrés Kelvin, mais c'était déjà assez froid pour ne pas détruire les noyaux. Okay, so the universe was like a nuclear reactor, and could make nuclear reactions like you find in a hydrogen bomb, or in nuclear. Yeah, I should be careful and say we don't have nuclear reactors like that on Earth, but we have nuclear reactions in the stars today, like in the sun today. Sorry. And these nuclear reactions, these nuclear fusion reactions, so the joining together of nuclei, nucleons, the protons and neutrons, to form the nuclei. These fusion reactions continued until about 340 seconds after the Big Bang. So that's between 5 and 6 minutes after the Big Bang. But after that time, the temperature had dropped enough that it was actually too cold to still much more than 1 million degrees, but cold enough that you could not form these you could no longer form these nuclear reactions, fusion reactions, to join the nuclei together, and so they stopped quite abruptly. Peut-être je vais juste préciser que les réactions nucléaires, ici, il s'agit de fusion, ça veut dire enjoindre, enjoint les nucléons, les protons, les neutrons ensemble. C'est le même processus qui a lieu au centre du Soleil aujourd'hui, mais c'est différent que les réactions nucléaires qui se trouvent dans les centres nucléaires ici en France pour générer l'électricité. C'est bien différent, mais quand même c'est le même qu'on est dans une deuxième génération de bombes nucléaires, les bombes à hydrogène, comme expliqué ici. So at the end of this critical period of just less than 6 minutes, right? The universe consisted of hydrogen, consisting of about 3/4 of the mass of all the ordinary matter in the universe at that time was hydrogen. And about 24% was helium in its most abundant stable isotope, helium-4, with 2 neutrons and 2 protons. The rest was another isotope of hydrogen, which is deuterium, 1 proton and 1 neutron. And which was small but still significant at 1/100%. So 1 part per 10,000. And even less of other isotopes of helium and the principal isotope of lithium. So note that the Big Bang only produces light elements, very light elements, and even only trace amounts of lithium and tiny amounts of beryllium. So there, that raises the question. We don't have any carbon or oxygen or nitrogen, for example. So where did these come from? D'où viennent les éléments légers comme le carbone, ou plus légers mais plus lourds que les éléments légers comme lithium. D'où vient le carbone, oxygène et azote, etc. On va aborder ça plus tard. Okay. Let's do a little summary up to this point. So with our knowledge of cosmology, astrophysics, chemistry, geology, biology, etc., these fundamental sciences, we can address this question of the existence of life outside of or beyond Earth in a scientific way. This is the new interdisciplinary subject of exobiology, the exciting new field of exobiology that we're discussing. Cosmology is the study of the whole universe, its structure, its evolution. It's a science based on the theory of Einstein's relativistic gravity, general relativity, which is a theory of space and time. And it's a science based on the observations of astronomy. The universe is old, about 13.7 billion years old. Je vais corriger l'orthographie ici plus tard. Il y a un autre N dans année. The universe is big, very big, and it's potentially even infinite in size, if that makes any sense. It has at least 10 to the 22 stars in the universe. That's how many we estimate exist in the visible universe. And most of them are in galaxies that are far away from our galaxy. Our galaxy is called the Milky Way galaxy. It's a typical galaxy with about, it's actually several times 10 to the 11 stars. So il y a en fait plusieurs fois 10 puissance 11 étoiles dans la Voie lactée. Une galaxie bien typique, ce n'est pas une galaxie vraiment spéciale. The universe is getting bigger. It's an expanding universe. Our solar system is found in the suburbs of our galaxy, and where the closest stars are several light years from us. On a sort of speculative aside, I would say that this is a very good news for us, because it there are certainly places within our own galaxy, for example, near the nucleus of our galaxy, where the density of stars is much greater than in this here in the suburbs, and so it would become much more probable that you have neighbors that are neighboring civilizations on sort of nearby stars that are close enough that those your neighbor civilizations could come to your planet and invade you. Obviously, this is speculation, but it's speculation based on knowledge of astrophysics and the structure of our galaxy. So je précise que c'est bien la spéculation de ma part, mais la spéculation basée quand même de notre connaissance astronomique de notre galaxie. So there are three types of matter and energy in the universe. As we discussed, there's dark energy. We know almost nothing except that it's necessary for the to explain the expansion, the rate of expansion of the universe, the acceleration of the expansion of the universe. There's number two, the dark matter, which is necessary. Again, we don't know almost anything. We know almost nothing about it, except that it's necessary to explain the movement of the stars within a galaxy and the movement of the galaxies within groups of what we call clusters of galaxies. And then finally, the least important of all is the matter and energy normal or standard, which it's a sort of matter and energy we can study in laboratories. So je précise que c'est la matière et énergie, on peut dire standard, que nous pouvons analyser dans les laboratoires et qui est en fait le moins important de tous les trois types de matière et énergie. This normal matter or standard model matter is described by the standard model of particles, and it's so at energy levels that we experience on a sort of daily basis. So here at home, sitting in my living room, or even in my kitchen if I'm cooking on a hot stove, those are still sort of everyday energy levels. And this ordinary matter is then consisting mostly of just protons, electrons, and neutrons at its most basic element. In other words, we're just talking about the matter that you find in the periodic table. So, je précise quand je dis au quotidien, ça peut être, même si je chauffe quelque chose sur le four ou dans le four, c'est une énergie basse de la vie quotidienne. On ne fait pas les réactions nucléaires chez moi. Et dans ce cas, la plupart des énergies et matière est dans la forme des protons, neutrons et électrons. Il s'agit de la matière dans le tableau de Mendeleïev. So even today, by mass, it's hydrogen and helium that dominate the ordinary matter and the elements of the ordinary matter in the universe today. It's still around 3/4 hydrogen and 1/4 helium. Even though that in stars that process stars are changing that, but it's a slow process, and so even today we still have about 3/4 hydrogen and 1/4 helium. So je précise en français que même si dans les étoiles, on change cette proportion de hydrogène et hélium, n'est-ce pas? Mais ça, c'est un procédé très lent et quand même, on a toujours aujourd'hui à peu près 3/4 hydrogène et 1/4 hélium dans l'univers aujourd'hui. Interestingly, only hydrogen and helium and a very little, minuscule trace amounts of lithium and beryllium were created during the first, less than 6 minutes after the Big Bang. And you have to wait millions of years after this Big Bang to form the heavier elements. And you do so in the first stars. The elements that are important, if not essential for life, life at least as we know here on Earth, it's the only life we know, is made of carbon and hydrogen and nitrogen and oxygen and phosphor and sulfur. These form in stars like our sun. But only in their last phase of life when they become red giants. So this motivates our future study of the life cycle of stars. So je précise, ça fait une motivation pour nous d'étudier les étoiles et le cycle de vie des étoiles pour comprendre l'origine de ces éléments plus lourds. OK, on arrête là.